Test. Test.
What?
Testing, testing.
Cool.
Alright, hello everyone. Welcome if you have just tuned in. So, yeah, I think should we start or should we wait a couple more minutes for more people to tune in? Harry, what do you reckon? Yeah, we're just waiting a few minutes. So yeah, I mean, whilst we're waiting, you should have a Jupyter notebook which has the policy gradients notebook open inside of it.
Show that is on the web app.
Yeah. So if you're wondering how to access today's materials, go to theaicore.com, log in. If you haven't logged in, make an account. It's pretty quick. And then here we go to code, deep reinforcement learning, and this is the third session. So this is policy gradients. Oh, the stuff isn't there on policy gradients, Harry. Okay. Okay, just go on the previous week's session. You should be able to click link to code, and it will bring you to here. From there, you can go onto the reinforcement learning repo, and you just get policy gradients notebook instead of the DQN one. Okay. So yeah, just get this up in front of you, and Harry, how can I write in the comments? Can I write in the comments?
Yeah, you can. But you have to do it through the web app.
Okay.
Is it being recorded?
Mhm. Says it's noisy. It's probably. I'm gonna fix the noise in the back. Right, yeah, guys, sorry about the teaching lobbies thing. You know, we can still teach today, but the teaching lobbies and the that kind of, the group lobbies, that's what they're called, they still need a bit more of engineering work, so you won't be able to use them today, but hopefully next session, which is this Saturday, you should be able to use them. What, group lobbies? So yeah, group lobbies is a feature that we're building into our online classroom, where you're going to be able to chat to other people inside here. Okay, that's a bit broken. Well, essentially, you're going to be able to talk to other people in your class using voice chat, and the hope is that I'm going to kind of give you some little tasks or questions, and you're going to go and talk amongst each other in these little groups and try and come up with some answers and kind of learn from each other as well as us. All right, I think. Let's get started. Okay, so before I begin, I want to do a quick recap because I know we've had a couple weeks of break essentially while we get this stuff set up. So I want to ask some questions and I want you guys to answer them inside the stream. So. Question 1: what is the difference between reward and value? Just basically, any of you just put the answer in there. I just want to do a recap, but I want you guys to answer it. Harry, are you going to be able to see if people reply?
Yeah.
So,
can you zoom in? And there's a strange noise. Apparently.
There's a strange noise.
What kind of noise?
Is there an echo? Is anyone having troubles with the sound? If you are, like, make a comment so we know. Yeah.
I'm gonna have to close this window.
Yeah, I think that was the door. But yeah, sure.
Maybe it's your laptop.
Yeah, it could be my laptop. Yeah, sure. Has anyone wrote any answers in?
Laptop fan. No answers.
Come on, guys. Why is there no answers? Sorry.
I don't see the question.
Okay, let me write it in here. What is the... Okay, someone answered right there. Who is that? Return is the sum of all future rewards discounted. Yeah, exactly. Well, yeah, I guess. Yeah, you have discounted value, and you just have return, which is the sum of all those rewards. Okay, cool. And whoever's answering that, is there a difference between return and value of a given state?
I'm going to post these questions in the chat.
Okay, cool. Well, you guys can answer it and you can figure it out. And yeah, I'm just going to get on with today's lesson. But yeah, that's just there. You can read the comments and get a bit of a recap. Cool. So, I guess this is already kind of a recap. What is the goal of reinforcement learning? The goal is to maximize the goal of the agent within the reinforcement learning problem is to maximize its expected reward over its lifetime. So a trajectory is essentially one. So actually, I'll ask a question: what is an episode of a game? Does anyone remember that? Nice. Yeah, that's a good answer. Return.
Tell people that they can reply to the comments by clicking the reply.
Yeah, and you guys can also click the little reply arrow and be able to reply to the comments. Yeah, I don't know. That's fine. I play through the terminal state. Yeah, exactly. One episode is from, we start in this game and then we play it until we reach a terminal state. And that is one episode. And the data we collect, i.e. that experience that we collect, is called the trajectory. And the trajectory is composed of a sequence of states, actions, and the rewards that follow. So, we can formulate this as shown here. J, which is our objective, parameterized by our policy, in this case, theta, is the expectation over the return of a given trajectory. And these trajectories are sampled from, basically, they're sampled using our policy. So, these experiences are collected using, whatever policy that we have. So what is a policy, actually? I want to ask that. Does anyone remember that? Anyone got an answer for that? What is a policy?
What actions take in a state?
Nice, yeah, someone's got the answer. So it takes in a state and it gives you an action. So a policy is essentially how you behave. So yeah, the objective, which we want to maximize, is equal to the expected reward that we receive by following policy pi, leading us along a trajectory t, not t, tau. Okay. So what we want to do is find, essentially, we want to try given that we're doing policy gradients, we want to try and solve for this policy thing directly. So until now, what we've been doing is trying to calculate values, for different states, and then figuring out how we can use that to inform a policy. Whereas now what we're trying to do is parameterize our objective and solve for the policy directly without having to calculate these value functions. Okay, cool. So this and this is doable as long as our policy is differentiable. So essentially, if I have a policy which is something like, let's say, a neural network, which is a differentiable function, then I can simply take the derivative of my cost with respect to the parameters of my neural network, and I can actually use gradient descent to keep on improving my policy and optimize it. So this shows that derivation. Okay, so we start out like this, which is what we had up here, and then we simply use this identity here to change it from an expectation to an integration over all different trajectories. Okay, so these two are mathematically equal. Okay, yeah, so since differentiation is linear, we can just basically pull this out, pull this integration sign out, and put the derivation inside here, the derivative inside. And again, so what we're trying to do here, right, is we're trying to get this in a format where we can use the log probability of a given trajectory instead of the actual one, and the reason is, okay, we don't actually have that derivation here. Yeah, so we bring the log back. We bring the log in here by using this identity, and once we've done that, we can simply use the identity that we used earlier to get this back into an expectation, and then we can kind of discretize it by, instead of using this expectation symbol, we can essentially take it as a sum. Basically, we can take the samples, the trajectories that we sample, we can use those essentially, because an expectation is a mean, right? So what we do here is we use all the trajectories that we've sampled, and then we just take the mean by dividing by n of that. Okay, and yeah, once we've done that, that basically means that we can calculate this derivative of the costs using essentially trajectories that we've actually sampled in the real environment. So what we've essentially done is we've gone from this, which is kind of it's not something that's directly implementable in code, into down here, whereas this, we can actually implement this in our code. So the derivative of our cost is equal to 1 over n, which is the number of episodes we have, times the log probability of a given trajectory multiplied by the reward of the trajectory. Okay, so actually I'm going to try and explain this step a bit more. So our objective, right? Our objective is basically a measure of how good or bad our particular policy is. So inside this integral, we have so this here, pi theta of tau, is the probability of going on a particular trajectory under our current policy. The second term is the reward given along that policy. So in order to maximize this, what I'd have to do is, for the trajectories which have a high reward, right? So this thing here can only be between 0 and 1, right? So if the reward is positive, I'm going to want to maximize the probability of that trajectory happening. Whereas if it's negative, I'm going to want to set this equal to 0. So essentially, we have come up with an objective here, which, you know, is essentially, yeah, the probability of a given trajectory multiplied by the reward of that trajectory. Does that make sense? I'm going to see if there's any questions. I'm sure there is. I want you guys to tell me if any of these steps doesn't make sense.
I think you should clear your cache or something, because the styling shouldn't be like that.
It is. How you pulled a pie out of nowhere. What is that? I can't really see that. A pi theta. So where are you talking about this line? Whoever said that comment, I'm confused about how you pulled a pi theta out of nowhere. I guess you assume that's what this is. Well, yeah, so this pi theta, okay, is pi theta is pi is a policy, okay, and theta is a policy which is parameterized by theta. So that's where that comes from, because here, when we're doing this expectation, we're assuming that tau, i.e. the trajectories, are sampled according to our policy, i.e. because essentially, depending on which policy I have, I'm going to sample different trajectories. If I have, you know, a terrible policy, I'm going to sample from trajectories which have a really low reward. Whereas if I have a great policy, I'm going to sample trajectories which have a high reward. So that's why our objective is related to basically pi of tau. And then when we do this step, we'll basically call our policy pi theta, because it's a policy pi and it's parameterized by theta. Because the expectation part entropy and policy gradient. So pi theta is the probability of a certain trajectory occurring under the given policy. That is correct. Yeah. Exactly. Is the same as the rain up. Same as the original expectation. This question, sorry, where can we download this repo? Oh, okay. I'll sort that out quickly. Actually, Harry, can you reply to that, please?
Yeah, sure.
Please explain the concept of entropy. What do you mean by that specifically, like in here? Because I don't think we've made any mention of entropy in here. Oh, I see what you're saying. Does anyone have any more questions about this? Is anything still not clear? Okay, Harry's going through and answering some of these. I'm going to keep moving on. Yeah, okay. So once again, real quick, the derivative of our objective with respect to theta is equal to the derivative with respect to theta of this objective, where this is the log probability of a given trajectory multiplied by the reward of a given trajectory. And there's a pretty important reason we do the log probability of this. Essentially, when we expand out this, which, you know, the probability of a given trajectory under our given policy, basically what ends up happening is that there's two factors which affect the probability of a given trajectory happening. So essentially, it's the probability of you know, starting in a current state, okay, multiplied by the probability of you taking a given action from that state, and then multiplied by the probability of seeing, you know, some next state, given that you took that action, right? So that part, so there's two components to it. There's a component of the transition dynamics of the environment, i.e. the probability of a next state happening given that you're in a current state and you take an action, and there's also the part which my policy contributes to, which is a probability of taking a particular action from a given state. And because we have this log here, what that means is, instead of, you know, multiplying these out all the way, the log means that I can just sum the logs, and because of that I can easily kind of cancel them out, like cancel out the ones that aren't relevant to my policy, because the derivative of my cost with respect to the transition dynamics, right, like derivative of theta with respect to my transition dynamics is just going to be 0, because my theta doesn't affect the transition dynamics at all. So this log, that's why it's important. And you know, before the next time we do this, I'm going to add an extra derivation of that right here. I'll just check for questions anymore. Okay. Alright, cool. So given that we can compute the cost of a given basically we can compute the derivative of our cost with respect to our parameters, you know, this thing, we can now just use gradient ascent, I guess, instead of gradient descent, to update this so that we keep on increasing, we keep on moving. Oh, wait. Yeah, Jay, this is this is our objective, not our cost. So what that means is that we ascend it instead of descending it. So yeah, this is basically the standard gradient descent formula, but with a plus in here instead, because it's ascent, not descent. And this, as you can see, this part just comes from right here. That's the derivative. So we just chuck that here, you know, we multiply it by a learning rate, and then we shift our policy parameters such that they move in a direction which slightly increases our objective. So yeah. So we shift the policy parameters, these are our policy parameters, and we shift it in the average direction that increases the log probability of taking a trajectory proportionally to how large the reward along that trajectory was. And it's called reinforce, which is this lovely acronym: reward increment equals non-negative factor times offset reinforcement times characteristic eligibility. Even I don't get that, so it's fine if you don't. Cool. So this okay. Let's take a let's just take a few minutes break. I want you guys to basically just reread through this, make sure it all makes sense, and we're going to start coding in a couple minutes. So let me just change that to this is not a code break, but we're gonna start coding in a sec. So yeah, just have a read through this again. Make sure you you ask some questions. If we compare the second level, what are the pros and cons between setting the learning rate to high or low? Okay, you just reply to that. Okay. Gradient. The derivation of the log pi quick question to everyone. Can you see the questions properly? So if you're on the AI Core website and you're inside the classroom, like so, my questions are kind of coming up all bunched together at the bottom. Let me know if that's happening to any of yours. Okay, so I've actually got my question section working in. If I go on Mozilla Firefox, it works. I don't know what that's about. Okay. Yeah, I'm sorry if you're having problems with that. We should. Oh, okay. I was going to answer that, but that's cool. Was gonna. Alright. If we're ready to go, let's continue. So what this is right here, it's just a little class that we've created, which takes in. I'll just show you how it's used. So it'll be like my neural network is equal to NN, and I can use this to create what's the word? I can use this to create neural networks of different architectures basically really easily. So I can write so let's say 10, 100, 15. Okay, and what that's going to do is going to make me a neural network which has an input layer of size 10, one hidden layer of size 100, and an output layer of size 15. And I can easily change the architecture of my neural network just by changing that list. So that's why that is there. Okay, so I'm just going to run that. Okay, well, so today, yeah, we're going to be using Griddy ENV. For those of you who remember that, well, for those of you who don't, it's basically a little 4x4 grid. We have an agent who at each time step can choose to move up, down, left, or right. and it has to try and get to the goal state, which has a little green, food on it. Okay, so what I want you guys to do now, so I'm going to run you quickly through this, and then I'm going to give you guys a little break to work on it, and then we'll reconvene and go through the answers. So I've got this function here, which we're going to use to actually train a policy gradient agent, and it takes something. So first off, we need env, that's our environment optimizer, that's the torch optimizer object that's gonna be used to improve our neural network through gradient descent. Our agent tag, so I think we use this for logging to TensorBoard. So in TensorBoard, when we see different agents training, we'll be able to tell them apart. Epochs, how many epochs do I want to train for? Episodes. And then how many episodes do I want to train for in each epoch? And then these two, don't worry about these for now. These are flags that we're going to use to specify whether we should use a slightly more advanced version of this basic algorithm that we're going to implement later on. Okay, so currently, they're both false. Baseline, false. 0. Okay. So for epoch, in range epoch, we set the average reward equal to 0. We set our objective equal to 0 to begin with, right? So what I'm going to do is I'm going to do, capital N, let's say, number of episodes. So I'm going to sample some trajectories now from the environment using my policy. So yeah, I set that 0 to begin with, and I keep on adding to it at the end of each episode. So okay, so I set done, i.e. that's basically a flag for whether this current game is finished yet. I set that equal to false because we're not done, we've just started. We reset the environment, and then we create a list to keep track of our log probability, the log probability values, i.e. this. And yeah, our rewards for that particular episode, it's an empty list to begin with, and we keep on appending it at the end of each step. The number of steps in this particular episode, 0. So while not done, what you have to do is, because we're using PyTorch and we're using a neural network, you're going to have to get the state which is returned from the environment and convert that into a format which is suitable to feed into our neural network, into a data type. And then, because the state of this environment is 3-dimensional, our neural network takes in a single vector as an input. So we're going to get that 3-dimensional array, and we're going to flatten that into 1-dimensional vector. So we use our policy network here to calculate the action distribution of our agent, i.e. Given the current state, what action should I take? We compute that. We sample from that distribution using what's called a torch, what's called a multinomial distribution. Torch has a specific implementation of it. You should look it up there. Torch distributions, multinomial. After we've sampled the action, we convert it into an integer, and then we send it to our environment. So we actually take this action. Once we've taken this action, we get our new state back, we get a reward back. We append the reward to our list of all the rewards. We set state equal to our new state, and then I want to append to here the log probability that my policy gave for choosing this action. And yeah, add one to the step. If done, break. If the game is going on for too long, should be break. Okay. This thing here calculates our average reward. So now for each time step, we calculate the total reward, i.e. the return that we got from this episode, and we add to our objective basically the log probabilities that we got multiplied by the weight, i.e. by the return of that. And then basically once we break out of this loop, we calculate the objective, the average objective over all these episodes. We invert it because PyTorch, when we do PyTorch works with gradient descent, not ascent, so we basically invert our objective so it performs descent on it instead. And then like usual here, we calculate the derivative, we update our parameters, and then we set the gradients back to 0. And this is just a little piece of code to visualize our agent, so we can see what it's learned after the end of each epoch. So yeah, I think that should be good. Whilst this, I don't think we even really need this, but this is basically saves our neural network. It saves our policy into a file in case we want to load it in at some other point. Okay, cool. So I'm gonna give you guys, let's say, 10 minutes to work on this. Make sure you put in any problems that you're having, like you ask some questions. Do we have screen share capability at all?
Not yet.
No, okay.
But it'll come with the group bodies next session.
So what's gonna happen? So for now, you guys, just work on this. Try to fill in these lines of code. Make sure you ask any questions you have in here. Next time we do this, we're going to be able to like screen share and help you, but for now, you're just going to have to do it without our help, I guess. Only questions. Alright, cool. So what was the question that this person's talking about? The one on update rule. Where is this question, person? Alright, person who question with the update rule, your question has been answered. Why do we perform an update with derivative? So yeah, why do we perform the update rule with the derivative of the objective? Well, because that's the gradient descent update rule, right? What we want to do is get our parameters, theta, and then update them with the derivative of our cost with respect to theta, and that's what this is. We get that from here. So yeah, that's why we use it, because that's literally the definition of gradient descent. You move in a direction of the you move in the opposite direction of the gradient. So yeah, that's why we do it with the derivative, because that's the gradient. Alright, it's code break time. Alright everyone, we're back. This is, yeah, let's get this coding done. Okay, so first line we need to complete is right here, which is we need to convert our state, currently it's a NumPy array, into a suitable data type to be used with PyTorch. So can anyone comment what this line should be in the comments right here?
Is your Starling working now?
Oh, on Firefox, yeah. Does anyone have the answer? Anyone?
Even part of it.
Even
part of it. Any part of the answer.
Yeah, any part of the answer. Does anyone have a clue? Does anyone even have a word that they can write in there which could lead me to the correct answer or remind me any way of the correct answer? Does anyone know anything about this line? If so, write it down. I want to see it.
Someone said something.
Did someone say something? Nice. Whoever. We should get these people's names up to it, because that'll be good. Yeah. Well, whoever said that.
Right now.
Great job.
Fire
There's a fire emoji. Yeah.
emoji.
Oh. Alright. Next thing we need to do, right? So, does anyone know or remember what the shape of the observations from Grid ENV are? Does anyone remember that? What's the size of the grid? How is that represented? How many channels is there? Right, never mind, we'll just go through it. So essentially, the shape that this comes in is a 3 by 4 by 4 tensor. So what we need to do is create, we just need to flatten that. So I say state.view, and the shape that I wanted to take is the product of, what is it? State.shape. Yeah, so the shape of my state is 4 by 3 by 3. So if I multiply those three, I'll get the total number of elements, i.e. the size of what it should be if I was to unroll that into a vector. Okay? So now we get our action distribution from our policy. So to do that, I just do we're gonna have defined a policy down here. So I'm just gonna use that. Where is it? Policy of state. I need to sample, so that's going to return me an action distribution. So I need to get a sample from that. So I'm going to go to there. I'm going to look that up. Okay, so what we're going to use is a categorical distribution. Okay, so my distribution is equal to torch.distributions.categorical. So all I have to do is write dot categorical, and all it takes is a distribution. So I pass it in my distribution, and then to sample from that, I simply I create the distribution, and then I do dot sample to sample from it, I believe. Yeah. Cool. And then I just get that. It's going to return me, a one element tensor. So I just do action.item to get the actual integer from inside there. Once I have that, I hope you're all keeping up in here. Cool. I'm going to do my environment, which is env, and I'm going to do dot step. So take that action which I just sampled from my policy. Okay, once we've done that, we need to append the log probability of that action. So who can tell me what goes on this line? So what I need to do is compute the log probability of taking that action and append it into there. I'll just give literally a minute if anyone has got an answer. Anyone? Come on. Anyone can even have a guess as to what it would be? Okay, no problem. Nobody's got a guess. It would just be, what can I do? I could just do torch.log, and the thing that I'm going to log is I'm going to get action distribution, and I'm going to get the action, the index of the action which I actually took to get the probability of it, right? So this gets me the probability of the action that I just took, and then I just log that, and I append it there. Okay, yeah, that's fine. Okay, so what is the weight here, right? So to calculate the objective, I need to work out basically the return from this, i.e. the reward of the trajectory, right? So I simply, the reward of my trajectory is equal to the sum of rewards. And now for basically, okay, cool. So now I'm iterating over each action that I took, and I'm just gonna add to my objective my weight multiplied by the log probability of taking the action at that time step. Okay, and to average it over episodes, so there's how many episodes? We do 30 episodes at a time, so I need to divide that by that, and then I'm just going to times it by -1 to invert it. Okay. Okay. Cool. So now I've calculated my objective, right? So I've got this objective here. What I've just calculated is this. So now what I want to do is take the derivative of that with respect to my policy parameters. So I just do objective dot backward, right? for those of you who remember that just computes the gradients for me. And then I just do optimizer.step, then gradients.0grad. So this will do the gradient descent step, and then this will reset my gradients so that next time I calculate them, they're not affected by my current estimate. Okay, so this is just going to be visualizing it. So again, we're going to need to copy what we wrote up above. Torch.tether state state.view state. Yeah, guys, comment if you're not following any of these. Literally, you can literally just comment the line number, which does make sense to you, and we'll go through it again. Oops, no, this is the wrong thing. Alright, cool. So now we're at the bottom here. So this line, I forget. Oh, no, I don't. So I'm gonna create this summary writer object, which is summary writer is what we imported from TensorBoard, and that's basically gonna create nice graphs showing the reward of our agent over time. So I'm gonna create a summary writer object. My env, what is my env? What is this, Harry? Create grading with time penalty?
I think it has a flag, time penalty.
Okay, so time penalty, what equals true? Okay, so time penalty is something which is going to change the reward structure of that environment so that we basically get -1 reward for each time step that we're not at the terminal state. Okay, I create my policy, so I need to do NN. What's the input size going to be? Does anyone know that? Can someone answer that for me? So is there, what are the constraints on this network? Does it have to have any particular input shape, any particular number of hidden layers, or any number of particular outputs? Can someone tell me that? Okay, someone asked that. What is the point of the writer object? We're going to use this writer object to basically send data to TensorBoard so that it can create graphs for us. So I'll show that in a sec. What is this 32? Someone wrote 32.
Line 32.
Oh, line 32. So yeah, whoever wrote this question, are you referring to line 32, or are you trying to answer 32 to the question about the shape of the neural network? It'd be good to get that clarified. I doubt it's about the line, because I feel like...
The observation space.
Right. Cool, yeah, that makes sense. So our inputs, the number of inputs that we have has to be... the shape, basically the flattened shape of our observation space, and we had calculated that already earlier. It was, is there a way to calculate it here? Yeah. So np.prod. So first off, we're gonna get env.observation space dot shape to get the shape of the observation space. and that's going to return us 3 by 4 by 4, and we do np.prod to multiply those three numbers together to get our the shape of our input, the size of our input layer. And I'm going to create, I don't know, a size 32 hidden layer. And then what about my output shape? What does that have to be? Does it have to be anything? Number of actions. Nice. Yeah. And the number of actions is env.action space.n. Alright, so let's train this bad boy. Invalid syntax. Okay, this, don't worry about this. You know what, you can just hashtag that out for now. No, wait, I'm all the way down there. Line 19, I have an error. Where's my error? Invalid syntax. Oh, here, I'm an idiot. I didn't complete this, so that should be env.step action. Oh man, so this is for saving it. I actually don't remember exactly what was written there for that.
You just put the actual model instance there.
So here, yeah, I'm going to put the instance of the model. And the state dict is policy.state dict to get the dictionary with, of the weights, and then to actually save this, save. So we create this dictionary which has model and state dict in it, and then we do torch.save on that checkpoint, and we need to give it a name. So what's the So yeah, I'm gonna get it inside an agents folder, trained agents slash agent tag, right? And yeah, and usually we call these files .pt, but you don't have to actually. So okay, we're still wrong. Oh, we need a comma right there. Oh, I haven't completed this time. So optimizer, what optimizer we're going to use? We can use torch.optim. Here it says use Sgd, so we're going to use an Sgd optimizer with our given learning rates and our weight decay. Oh, and this, for those of you who are getting this error, I think this has to be lowercase n. Oh, once again, I'm an idiot, because the first thing that you have to pass into the Optim Sgd object is the actual neural network parameters that we're trying to optimize, and then the learning rate, and then the weight decay. Oh, one other thing here, when we're creating our neural network, because the output we're expecting is a probability distribution over actions, we need to set here distribution equals true. we need to set that flag equal to true. So distribution equals true. Here, log policy is an array, and I'm trying to index that, so we've got to use square brackets, not round brackets. And yes, it's training. Okay. How's everyone doing with that? Has anyone got it working? The weight decay parameter is the parameter we use as for regularization. Basically, in regularization is something that's used to improve the generalization of your model. So this we actually already cover. If you go to github.com/ai-core, or actually if you go to the ai-core.com, I think it'll be even more accessible there. I'll log in. If I go to code, deep learning, and you go down here, intro to regularization. Oh, shit. I think we renamed this. But essentially, if you come to the AI core, the Strong ML Foundations repo, and there's something here called regularization. So yeah, check that out. Any more questions? Oh, cool. Okay, so I'm just going to comment this out because I don't really care if it saves it or not. Alright, cool, so we're able to get this to do pretty well. Now, can we get it to solve a slightly harder environment? So the one we're going to use now is called cartpole. So to do that, you just have to do gym.make, and then in here you do cartpole-v0. And that's going to load this other environment. And here, because of the way we've written it, we've written it in a nice and parametric way. So here, all I need to do is change the input size and the output size of my neural network, and everything else should work exactly the same. So the idea here is that we can move left and right, and we have to choose actions such that we balance the pole on the card. Maybe we'll let that train a bit longer, see what happens. So yeah, if you leave this running for long enough, it will eventually learn this. I guess it's just pretty slow to learn. Yeah, and back to a question that someone had asked earlier about using TensorBoard. So if I just go to the directory where this file is, I can just go tensor board -- logger equals runs.
Can you zoom in?
Sure. Oh. Just gonna empty that real quick, and now I'm going to restart this. So yeah, this is basically the reward of our agent over the episodes, I believe. Yeah, so this is over the number of episodes, and we can see there is a kind of, you know, it seems to be improving. Refresh that. Oh. Okay. You see, yeah, it is able to improve, but it's quite kind of noisy, or at least it varies a lot in how well it's doing. It's not just kind of consistently improving. So that's called, you know, reinforced. It's called vanilla, you know, policy gradients. So how can we? I mean, before we move on, any questions? Any questions? Hmm? The training was. So how many epochs would you need? And this is kind of dependent on exactly what task you're doing, and it's also stochastic, right? Like you said, we're sampling this. So if we sample good actions, we'll learn quicker. If we sample bad, we'll, you know, learn slower. So how many epochs would we need for it to converge? Yeah, it's kind of variant. But yeah, for this game, I don't know. Basically, this is going to keep improving until it beats the game. And the point at which you beat this particular game is when you've earned 200 reward. So if you stay alive for 200 time steps, the game ends. So, you know, I don't know exactly how many epochs it would take for the agent to learn, but over time it would converge to hopefully to get that. Okay. So one little improvement we can make to our learning algorithm. Okay, so yeah. So looking back at our, you know, original kind of update rule slash, you know, yeah, slash objective. We're looking at our objective right here. When the reward of a trajectory is positive, we're going to increase the probabilities of it. That's what this does. Okay, so yeah, consider a game where for every, you know, whatever I do, I get, let's say, 5 reward, okay, per time step. But then there are certain things I can do to get me 100 reward. And these, you know, these 5 reward actions might actually be the worst, you know, kind of actions that you could take in the game. But because they're positive, our objective function is going to is going to push them up the probabilities for those trajectories, simply because they're not negative. So this basically, this kind of causes a problem where, if I have the kind of same reward function but I offset it by a certain number, my policy is going to either encourage or discourage actions just based on whether they're positive or negative. Whereas what we really want is, we want to push actions, we want to increase the probability of actions which are better than average, right? Because if the average reward, let's say, is minus 100, and then a good, the best reward that I could achieve in a given environment is -1, then I don't want to decrease the probability of the actions which lead to the -1 happening. Rather, I want to increase them, because they're the best actions I can do relative to this whole environment, because the average I expect to get is -100 per time step. So what we want to do is, we want to do something called like baseline, where we essentially renormalize this the reward of a given trajectory with respect to the average reward I actually achieve in this environment. So this it centers the distribution around rewards across all the trajectories I've received. The distribution of rewards across trajectories around 0. So essentially, this centers the rewards that we get around 0, such that some actions, the better actions, are encouraged and the less good actions are discouraged, rather than positive being encouraged, negative being discouraged. Okay, does that make sense? Similar to gradient boosting. I don't think it's quite like that. That was just in response to this question. I think in the way that gradient boosting uses kind of this normalizing is not the same way here. Okay. And a baseline that we could use is the average reward that we have received from any trajectory, essentially. Okay, cool. So that's one change we can do. Another one that we can do is called causality. Okay, so before, if you look at what we're doing in our code, as we're going through each log probability, the log probability of each action we took, and we're multiplying that by the sum of the rewards for that whole trajectory. And this doesn't quite make sense, in the sense that, let's say my game is 20 it's 20 time steps long, and so let's say my game is 20 time steps long, and let's say for the first 10 time steps I'm doing really bad, and then for the second half of the game, the final 10 time steps, I do really well. Okay, so what I want to do there, right, is like the actions which are from the 10th time step onwards, they're going to be weighed by the sum of the rewards of that whole trajectory, right? And that doesn't quite make sense, because the rewards that I got before taking those actions couldn't have contributed. The actions that I take after the 10th time step couldn't have contributed to the rewards that I got before that time step. So what we want to do is something called causality, where we only weigh the log probability of a given action by the rewards that are received after that, because only those rewards are the rewards that this action could have impacted. Okay, so that's the two improvements. This is the equation for that. So considering all the trajectories. So yeah, so I'm looking across basically. So I'm looking at each time step and the trajectory. I'm getting the log probability of taking the action at that time step, and I'm multiplying it by the sum of rewards from that time step onwards, instead of from 0 to the end. And essentially, there are some challenges around combining both of these together. Yeah, and that's explained here briefly. Just have a look through that. But essentially, yeah, we can't combine these two things unless we do something else, which I'm not going to go through now. It's called actor critic, but yeah, don't worry about that. Cool. So now, guys, I want 10-minute break. So here, what I want you to do is we want to assert that because of what we just said, that we can't use both. We want to make sure that a person hasn't set use baseline and use causality both to true at once. So assert. So what I want to do is assert not use baseline and use causality. Okay, so this is just going to make sure that we don't have them both set to true. So then, yeah, just like before, we're going to be. So here we initialize our baseline to 0, and every time we receive a reward, we want to update our baseline. Okay, yeah, so pretty much everything is just like before, all the way up until here. Here is basically where the bulk of our change is. So if use baseline is true, what we want to do is average. Right here, what we want to do is essentially update our baseline with the new rewards that we've received, so that we can basically, we can update our running average of the rewards we've received, right? Any questions? Okay, no. And then, if we're using the causality, our weight becomes so down here, if we're not using causality, it would be the sum of rewards, but here it needs to be the sum of rewards from the current time step onwards. Okay, and then finally here, the weight is equal to the sum of our rewards. Take away what should be here is our baseline. So yeah, guys, I'll give you let's say 10 minutes to implement that. Make sure you ask some questions, and we'll reconvene. Alright, y'all. Let's get back to it. Okay, so does... I mean, where are we at? Alright, yeah. So here, this line, I'm gonna just fill in. This is called an iterative sum, Harry? What is it called? Incremental average. So this is called an incremental average, where instead of storing a list of the items you want to average over, you can just have one item, and then keep updating that with whatever new data you get, and it will keep track of the average. So I don't remember exactly how it's done, but right here.
Just copy that and show the equation.
Yeah. So yeah, to calculate the incremental average here, we say that the incremental average is equal to the current one, current average added to this shit, whatever. So yeah, that's basically this equation right here. So yeah, this is basically just calculating an average reward that we get over a given trajectory. Okay. Yeah, I don't know what to do about that. So, is anyone else having problems with the audio?
Upvote that comment. So.
Yeah, what should I do then?
It's fine, just tell everyone upvote the previous question. Could you fix the audio if it's bad?
Yeah, guys, if the audio is broke for you, just upvote this. Yeah, this comment right here to let me know.
No, the other one.
Oh, the other one. Wait, yeah, this other one. Alright. Okay, cool. So yeah, so if we have this baseline, right, we incrementally, update our baseline, and then who can tell me what goes here? So given the equation here, right, for baselines, we weigh each log probability by the reward of that trajectory, take away the baseline. So based on that, who can complete this line for me? Minus baseline, yeah, cool. Okay, cool, so the baseline one should be fine. So what about this one here? So if we were using causality, what would the weight be instead? Yeah, this is our weight, so what would that be? Nice job, guys. So what I want to do is sum. So I'm iterating over each time step, and I only want to get the rewards from the current time step onwards. So what's a simple way to do that? Sum of the slash rewards. I want you to write in there what you think I should type out. some. Okay, can anyone tell me about what they think about this here? Who thinks it's correct or who thinks it's wrong? I want you to reply and write a comment about it. Nice. Okay, yeah. We just got this here. So yeah, this was almost correct. But this was just getting the reward at a particular index. And the sum of reward at a particular index is just equal to the reward at a particular index. So what we need to do is get it from index, and we need to write this colon to get it from that index onwards. Okay, so I'm going to paste that in there. And our index is actually called IDX, not index, so IDX. Okay, all of that should be good, and this should be fine for saving it as well. Okay, so here I'm gonna try first one, use baseline equals true, and use causality equals false, and let's see how we go. I need a come on. Yeah, I mean, let's see how much yeah, this improves our algorithm by. Okay, so if I go on TensorBoard, I should be able to see. So this is the allegedly improved carpal. So I'm going to reduce the number of episodes. Actually, no, I'll just keep that. Yeah, let's just increase that. See how it does. Let me know how your agents are training. So what exactly do you mean by this question? Do you mean how would we compare how good two different algorithms are at, for example, completing carpal? Is that what you're trying to ask? Or just graph? Yeah, so yeah, that is what you're trying to ask. And yeah, so the way we compare these algorithms is by looking literally at how well they do on this game. And how well they do is just how much reward they get. So we can see, you know, the baseline, it didn't really improve it too much. It's kind of still, you know, about the same. Let's try it for So it seems to me, I mean, we'll find out from looking at this graph, that when we use baseline, it seems to do a lot better. It seems to be learning faster. The blue line is baselines, and the red one here, sorry, the blue line is causality, the red line is baseline. So we can see that causality seems to help a lot more with solving this task than baselines. Yeah, yeah, so literally if we're looking at this graph, we can see it's already, you know, it's starting to diverge. The blue line is starting to do kind of significantly better than the red by now.
Press the button on the left.
Yeah, that's not what I'm trying to do. I'm trying to get it to show the top of these spikes. Okay, yeah, as we can see, towards the end it's getting highly varying, but overall I think
Try and smooth it.
it's doing slightly better. Yeah, let's smooth this. But yeah, I'm sure if you leave these running, you play around with the parameters, learning rate, use causality, use baseline, maybe even the architecture of the network, you can play around with that, and yeah, eventually you will get to the point where it's just solving this game. Do you have any guide to using TensorBoard? Why is there so much? Do you have any guide to using TensorBoard? Well, TensorBoard is, yeah, it's pretty simple. I can literally go through it right now. So all we need to do is create the summary writer object. Well, yeah, so first thing we need to do is import summary writer from torch.utils.tensorboard. Then we create a writer object, and every time I want to add a point to my graph, I just do writer.addScalar. I can pass in a string, which is kind of which will, so that's the string here. So this string was cartpole, the string passed here was cartpole-improved, so that's just like a tag. I pass in the y value here, and then this is my x value, and that's it. I just keep on adding data points to that, and then if I want to view those data points, I just go to the directory where I'm storing this Jupyter Notebook file. I open it up in terminal, and I do tensorboard --logdir is equal to runs. That's the default, and when I run that, it's going to open up this where I can see all of it. Okay. Why is there so much variance in the causality graph result? So, why is there so much variance? Well, it's essentially to do with the fact that there's naturally going to be a variance in how well our network performs over time. Because here's the thing: we're using stochastic gradient descent, right? And what that means is that it's a stochastic process. So sometimes it's going to make a change to its weights, which is going to lead to a significantly improved kind of rewards, or it could make a small change which will lead to it doing worse. And it's kind of, it's just kind of varying in the same way that stochastic gradient descent is varying. Every update that you take in gradient descent doesn't guarantee that you'll see an improvement in the reward. It's just kind of overall, if you do it for long enough, you should see an improvement. Does that make sense? Okay. So yeah, that's pretty much it really. So what I'm going to do is show you this one final thing. So again, it's very easy to, because we've done it parametrically, to change what we're doing. So here, we're going to try this on a different environment called Lunar Lander. So gym.make lunar lander -v2, and sure, let's just run that, with baseline. Let's see how it does. This game is slightly more difficult, so it will take quite a while longer to train. And with regards to teaching, there's enough yeah, there's not much else to go through really here. I mean, yeah, I will just quickly fill in this here to show you what it is. But essentially, when we went up here, at the end of each training run, it was creating a checkpoint of our neural network. So if I go to here, sorry, agents, and we can see here, that's our trained agents. And, you know, so we can see here how to save them. How do we load them in while this thing is training? I'll quickly show you guys. So how do you load in an agent? Get model using model key. So env. Yeah, saved. So yeah, so what we do is we do torch.load of that file, and once we load in that file, we just say yeah, policy was equal to save model of model, which is the first parameter of what we save here. You see, model.
Like the NHS.
What? Oh, is it clapping time?
Yeah.
Yeah, guys, let's clap over the live stream for Corona. Jokes. Anyway, so yeah, we loaded that model and state dict. Well, what we need to do now is, yeah, so policy. So we get this neural network which we've loaded, and we do load state dict, and then we do saved model of state dict, I believe. Yeah, and then we just put our policy in evaluation mode, so .eval, and then yeah, this should work. For now though, let's catch up with how our mighty fine agent is doing. So we can see it has been improving, which is good, but it still hasn't managed to get a positive average reward, and the reason is because it's actually relatively difficult to get a positive reward in this game. If you're consistently getting positive rewards, that means you're very close to having solved this. So yeah, it is improving over time, which is good to see. Oh, yeah, it did. Yeah, I just had a sudden hit. Alright guys, yeah, so I'm just going to let this train for a little while longer. I'll probably stick around for another few minutes. If you have any questions, ask away right now. Next lessons should be hopefully much better, because we're going to, get this whole class lobbies and all these other features that we're thinking about for our live classroom. We're going to get all of that set up. So yeah, should be good. Meanwhile, yeah, thank you for coming. I hope you've learned something. Okay, where can I find the videos for the previous content? The code and link to the repositories. Yeah, this current course actually, we don't have an online, we don't have a recording of it yet, but that will be coming soon.
This is it. I will just release this.
Okay. Yeah. Yeah, maybe.
Or at least next time we run this course, we'll record this and then have it available.
Yeah, that should be good. So yeah, there's no previous videos right now. Actually, what about open hacking? Is that still on?
That will be launched this week. Yeah.
So this weekend?
Yeah, I guess so. I'm sure it'll be ready
Yeah, I mean, so guys, if you have any questions, and you want kind of, if you want to actually chat to us over video and audio instead of typing questions, then come along to Open Hacking, which is happening this Sunday. It's going to be our first online one. And yeah, it's not just for this, it's basically any questions you have, any problems, if you just want to come and just hang out, really, that's also cool. That's what Open Hacking is for. So yeah, make sure you come down. Yeah, that's good. Alright, cool. AI core out. We'll see you on the other side.